AQA, A-level physics, and this video for medical physics is X-ray imaging. So we're going to cover quite a lot in this video. I'm going to talk about the production of X-rays, like how an X-ray machine works and the X-ray spectrum, factors which affect the quality of the image, and how you actually produce an image and the different ways that that can be done and advantages and disadvantages. So, X-ray basics. What is an X-ray? As you should know, very high frequency, high energy electromagnetic waves. They pass through soft tissues like skin and muscle and fat very easily, and they are absorbed mostly by bone. We can use X-rays to produce shadow images of internal structures, like if you want to see if somebody's got a broken bone. Now, this is an X-ray tube, a typical X-ray tube, and electrons from a hot cathode. So our hot cathode is here, and it shoots out electrons. So you should know what an electron gun is. You should know about thermionic emission by now. And these electrons are accelerated by a very high voltage, maybe something like 100,000 volts in a vacuum. And then these electrons hit a metal target, and they will hit a spot on the target about there. And then stuff happens inside the metal, and that produces a cone of X-rays which comes out from the target like that. So fast-moving electrons strike a metal target, and that produces X-rays with a spectrum of energies. Now, this particular target, it's made of tungsten because it has a very, very high melting point. One problem is that all of these electrons landing on the same spot, that spot is going to get very, very hot, and the target is going to get damaged. Okay, so what do you do about that? Well, the target spins around very fast, and that means that the electrons aren't always landing at the same place. Otherwise, the target would be damaged. It actually gets pitted. It has a large mass, so that the heat is dissipated, it's spread out, and then the X-rays radiate from this beveled edge. This is the spectrum. Now, you've got this continuous spectrum, and you've also got the line spectra. I'm not bothered about the line spectra. That's characteristic of the metal. So those lines would always be in the same place if the target was made out of tungsten. Okay, the X-rays are produced when electrons are falling from higher energy levels, okay, inside the atom. If we increase the current in the filament, remember we were talking about thermionic emission. If we increase the current in the filament, then the filament gets hotter, and so there's more electrons dancing on the surface. There are more electrons emitted, and so you get more X-rays produced. So increasing the current in the cathode filament increases the intensity of the X-rays across the spectrum. If you increase the accelerating voltage, now, and this actually mentions this in the specification, the maximum energy of the X-rays increases. So in this diagram here, the maximum energy is there. If you increased the accelerating voltage, that would get bigger. It would maybe go to there. Again, the intensity across the spectrum will increase, and the peak of the curve will happen at a higher photon energy. This is interesting. This is an X-ray machine control panel. So whoever's operating the machine can just press a few buttons. There will be presets. So if somebody like an adult man comes in and he's broken his ankle, then you would press a button for that. But then you do have control over the accelerating voltage, the cathode filament current, Remember, that would control the intensity and the exposure time as well by pressing these up and down buttons. Now, attenuation. Attenuation means like getting smaller. If it's attenuated, then it is reduced. And if you look at this graph, it should be pretty obvious. For a particular material, if you had a uniform material and you did a graph of intensity of how much gets through against thickness, then you should recognize that's a kind of an exponential relationship, isn't it? And indeed, if you look at this equation, that should be pretty familiar. I equals I naught e to the minus mu x, where mu is a constant which depends on the material. And it's called the linear attenuation coefficient. So that's a property of the material that the X-rays are passing through. Okay, so just as radioactive decay, it kind of varies exponentially with time, here it goes down exponentially with thickness, because it's all to do with probability, whether an X-ray is absorbed or not. As X-rays pass through a material, they interact with electrons in the atoms. So in a denser material, the atoms are closer together, and so the chance of the X-rays interacting will be bigger. So these materials have a higher absorption coefficient. So we have this other quantity, which is the mass attenuation coefficient. We have the linear attenuation coefficient. If you divide that by the density of the material, you get the mass attenuation coefficient. And then there's the third useful quantity. You're going to get all these equations on the formula sheet, so don't panic. This is the half thickness. Now, again, this analogy with radioactive decay. The half-life is the time it takes for the count rate to half. The half thickness is the thickness of the material needed to absorb half of the X-rays. Now, that will depend on the energy of the X-rays. So you'll have like the half thickness for 60 electron volt X-rays. Okay, so it depends on the material, but it also depends on the energy of the X-ray photons. And the equation should look very familiar. It's not T half is log 2 over lambda, it's X half is log 2 over mu. This is an interesting table of, you've got different materials, different densities, different mass attenuation coefficients, 4 different photon energies. So you have a look at this table. What patterns can you see in the data? And then I've asked you to work out some half thicknesses for different materials for 80 kiloelectron volt X-rays. Okay, so patterns in the data. Obviously, from air to bone, the density is increasing. The density of fat and water and soft tissue is about the same. Obviously, bone is much more dense. Okay, for any particular photon energy, you will notice that for fat and water and soft tissue, there's very, very little difference between them. However, for bone, it's much, much bigger. And that basically means that bone is going to absorb lots of X-rays. And that same pattern goes down if we increase the photon energy. Okay, we will see that more of the X-rays will get through because the mass attenuation coefficient gets smaller. Okay, but the same pattern for these 3 tissues here, there's very little difference between them. For bone, it's bigger. If you're going to work out I asked you to work out some half thicknesses, and there you go. So I got for soft tissue 3.6 centimeters, and for bone, it's less than half that. Okay, 1.6 centimeters. Okay, what is a contrast medium? Now, if you want to look at, let's say, somebody's esophagus or somebody's stomach, The mass attenuation coefficient of the cartilage and the muscle, etc., is very, very similar. So what you can do is you can increase the difference, and that will improve the contrast. So you'll get a clearer picture. If you look at this animation here, and one example of that is called a barium meal. And what you do is you swallow this liquid, which is a solution of barium sulfate, and it's a very, very dense liquid, and it's swallowed by the patient, and that increases the amount of contrast, and it shows up on this X-ray. Looking at it, shows up as dark on the image. X-ray filters. Now, what are those? Now, the X-rays emitted by the X-ray tube show this continuous spectrum. Now, basically, we only want the high energy X-rays, which we call them the hard X-rays. The low energy photons, we're not bothered about them. They're not going to penetrate deep into the body. They're just going to be absorbed by the body. In other words, they're increasing the dose that the patient receives, and so that's bad. That's increasing the chance of getting cancer. So we don't want them. They don't reach deep into the body. They don't come out the other side of the body, so they don't contribute to the image at all. So if we can get rid of them and just use the hard X-rays, that would be great. So what we do is we use a filter, and the filter is usually just a sheet of metal, maybe some copper or some aluminium, and that absorbs the low energy photons. And so what gets through is just the hard stuff. If you look at the effect on the intensity, so basically the hard X-rays will get through, and then the low energy photons will mostly be absorbed. And that's a filter. We say it hardens the beam. Geometric considerations. If you look at this, you've got your focal spot, you've got the object that you're looking at. Let's imagine that's just a circle. And then on the screen, we're going to get an umbra, which is the shadow. And then we're going to get this penumbra around the outside. And that will look like a fuzzy edge. So the image won't be very in focus. You'll have this fuzzy edge around the image, which is this unsharpness caused by geometric considerations, geometric unsharpness. You can minimize that a few ways. So you have a small focal spot. You have a large distance between the spot and the target, and then you have a small distance between the target and the film or the detector. Okay, so you can control the amount of geometric unsharpness, these fuzzy edges. Another reason that the edges may be fuzzy is if the patient actually moves. If you're taking an X-ray over about 5 seconds, you don't want any movement whatsoever. So if you're looking at something which may be moving, for example, the heart, then a short exposure time with more energetic X-rays would be used. Talking about this X-ray beam, how do we control the field? In other words, the area that actually gets blasted with X-rays. So we use some kind of a collimator. A collimator controls the size of the beam. And the first bit of the collimator is probably just a lead tube, yes, so that only the X-rays that go through the middle of the tube are actually used. And then you have these two lead plates, and you can turn a knob, or it's done automatically, and you can change the size of the aperture between the plates. You can have a square or you can have a rectangle. Before you actually take the X-ray, there's a light bulb in the tube, and that shines, and then there's a graticule, this cross, and so you can actually see exactly where the X-rays are going to fall, and then the nurse or the doctor leaves the room and press a button, take the X-ray, perfect. So this is collimating the beam, controlling the field upon which the X-rays fall. Now, X-ray film is not used anywhere near as much as it used to be. There was a time that you would produce a thing called a radiograph, which is a bit like a photograph. So the X-rays pass through the patient and then they strike film, like photographic film. The film starts off white, but then it goes black when the X-rays fall on it. And then the X-rays, the intensity of the X-rays determines how black it goes. The X-ray film is coated with some kind of a silver compound, which is just the same as photographic film, old photographic film. And then once exposed, you have to process the film. If you did it by hand, then you've got to put it in like different chemicals, and then you've got to wash it and then hang it up to dry, and it all takes a while. And then once it's developed, then the doctor puts it on one of these light box things, and they can look at it and figure out what's going on. There are machines that do this, like this is one for dental x-rays. So you take x-rays of your teeth and then you just put the undeveloped film in this machine and press a button, and then after a while it comes out. Now, fluoroscopy, it means using a fluorescent screen, so a screen which has some kind of a phosphor on it, so that when the x-rays hit the screen, yes, then it produces light. These have been used for a very long time, in fact since shortly after x-rays were discovered. In fact, x-rays were discovered by accident because they were making some chemical fluoresce in the corner of the room, and Wilhelm Röntgen noticed it and realized that something must be causing this. That's how x-rays were discovered. So a fluoroscopic screen produces light, and then you can either just look at the light and see what's going on, like in this photograph, or that light falls on a photographic film. And if you do this, then you don't need as much x-rays. You can use a lower intensity x-ray, and then the patient doesn't get as much of a dose. Although I dare say in this photograph here, they're getting quite a large dose. An important improvement is image intensification. So what's happening on this diagram? So X-rays fall on an input phosphor. Again, it's like a fluorescent screen, and that emits light. And then you've got photocathodes that produce electrons when the light falls on them. Then you accelerate the electrons with a big voltage and you focus them onto another phosphorescent screen, the output phosphor, and that converts the energy of the electrons into light. And then you can have a TV camera or photographic film, and you can actually see what's happening in real time. Well, if it's a TV camera, you can see what's happening in real time inside the patient. An image intensifier, it actually makes the image up to about 5,000 times brighter. Okay, this system is much more sensitive than just using film, and so a fluorescent screen, film and a fluorescent screen, so a lower intensity of x-rays can be used. The image is up to 5,000 times brighter. So you can use a continuous beam of x-rays safely for up to about 5 minutes. So you can look at a patient's heart beating, or look at their lungs getting bigger and smaller, whatever. You can look at stuff for up to 5 minutes. Apparently after 5 minutes an alarm goes off and tells the doctor, the radiologist, switch it off now. And then lastly, a recent development since the 1990s, I think it is a flat panel detector. And you can think of this as just like the CCD in your camera. So you've got scintillation, you have a scintillating material. And again, a scintillating material, the x-rays fall on it and you get flashes of light. And then you have an array of photodiodes. Cesium iodide apparently is the yellow stuff, the yellow layer there. And then the x-rays create a charge on these photodiodes, and that's read and that's converted to a digital signal. Okay, better quality than an image intensifier. You can use a smaller radiation dose. The image produced is much quicker because there's less components in the chain. It's smaller and more rugged than the image intensifier, and you're producing these digital images. And once you've got a digital image, you can store it on your computer, you can email it, you can process it, you can increase the contrast, you can do loads of stuff with a digital image. So that's a flat panel detector, FPD.